So all the way down at the disk level storage, Amazon Redshift organizes itself like this. Imagine you have an order table that contains details about an order. There might be a shipping amount, a tax amount, a total sale price, any discounts applied, as well as tracking numbers, customer details, various dates, flags, and other types of information, survey information, all of these individual items making up a record of a single order. They are very important to each other in terms of an order, but maybe not in terms of an analytical type report. Typically in a data warehouse scenario, a report is rarely interested in something as focused as a single order, and all the nuances and demographic information that might come with that order. You're much more likely to want to know the total average of sales amounts for a given quarter, or the most common occurring zip code. The examples could go on, but nearly all of them, if you take a look at the data elements required to calculate the final output, would be focused on specific columns as opposed to complete rows. To support this, Amazon Redshift is what's known as a columnar architected database. The individual storage units on disk are made up of sections of columns as opposed to sections of rows. Further, with an analytical type database, when you do read data, it typically is going to span a much larger area of concern. So while a transactional database might have storage units as small as a few kilobytes, Amazon Redshift storage units of column data are 1 megabyte in size. And the benefit is this: when reading individual units of storage from disk into memory where it can be processed, the physical reads are almost always going to be the largest bottleneck, including the round trip to queue the data, bring it in, make sure you got it all, and communicate back and forth with your storage subsystem. And this is true even in modern solid-state drives. Reducing the number of round trips between disk and memory to obtain the data needed to satisfy a query is key. Now to illustrate, consider this example. Here at Abacus, we have a business need to produce the most popular selling item in our inventory weekly for a given year. But we sell millions of products a day. In a row-based database, I would need to read in each block that contains data that is critical to my query. And since they are stored in row-based pages, if I were using a common row architecture database, each page I read now contains not only the data I need, but customer names, coupon codes, addresses, sales agent details. Over millions of orders, unless I have a very focused index supporting the query, I end up reading massive amounts of data that I don't actually care about for my query. All of this extra data is being read into memory prior to the individual column of interest being stripped out and the rest of that data just discarded. With column storage, there are 3 columns I'm interested in: the product, the total sales, and the date. My query can read only these columns into memory and begin calculating them into groups. Additionally, as my analytical query is spanning weeks as opposed to something as focused as a single day or a single order, it finds further efficiency into reading in large 1 meg blocks, because each of these 1 meg blocks is far more likely to be almost entirely filled with data that is relevant to my query. So this is the theme. Typically, anything you can do to reduce total data read from physical storage is going to be better when it comes to performance. And this brings up another reason why columnar storage has a distinct advantage when used appropriately.